about extreme values. Okay? Extreme values. Extreme values of functions. Did I hit record? Are we recording?
Yeah.
We're recording. So, be good. So, extreme values of functions are just kind of what they say. The high points and low points are extreme values. So if you have some graph that kind of looks like this and goes up, and then has something like this and goes like that, okay? And it has endpoints. This has lots of extrema in it, okay? The lowest point, oh, I didn't want to do that. I wanted to go like this. Okay? This has lots of extrema in it, meaning high points and low points. If it's the lowest point in a function, then it is called an absolute or global extrema, okay? So this point right here, just from looking at the graph, that would be an absolute minimum or maximum? Minimum, okay? Minimum, also known as a global minimum, okay? And if it's a global minimum or maximum, it is also a relative one, okay? So it's both a global and a relative minimum, maximum or minimum. This point here appears to be a minimum or a maximum. This is and they call this a relative. They call this a relative, also known as a local maximum. Okay? And I have a relative max because my grandpa's name was Max. So he's my relative max. Hey, don't be a wise guy. Okay? So this is called a relative min. So notice here that I have something called the cusp. What do I call this? Is this what do I have here? This is a relative maximum, but is it the highest point in this graph? Okay? Not only is it a relative maximum, but it's also the absolute maximum on this closed interval. If I start at A to B, that it's the highest point in this closed interval from A to B. Okay? So this is also an absolute maximum. And what do I have going on here? What's this? This is also a relative max. Okay? Because all the points around it are smaller than it. Okay? And it's defined at that point. So this is a relative maximum, relative minimum, relative and absolute maximum, and relative maximum. So when you're doing these things, you always have to check at the endpoints. That's the thing that people always forget. Check after you find out where the derivative is 0 or undefined, which we're going to talk about. Then you also need to check what's happening at the endpoint. Now notice, at this point, the slope is what? 0, and at this point, the slope is 0. And, oh, I forgot this relative minimum right there, didn't I? Slope is 0. Is the slope 0 here? No, yet I still have a relative maximum. Is the slope 0 here? It's undefined, yet I still have a relative maximum. And over here, the slope is definitely not 0, and I have an absolute minimum. So the slope being 0 indicates that something is going on there. You might have a relative minimum or a relative maximum, but not always, okay? But there is some kind of critical point there, okay? But at a relative minimum or relative maximum, something is happening. What is happening to the slope at each relative minimum or relative maximum? And this is something that's important to understand. What's happening? So Connor?
Changing. positive.
Exactly. From positive to negative or negative to positive. Okay? So notice here, as I look at this, the slope is positive, then the slope is negative. As I look at this one, the slope is positive, the slope is negative. Here the slope changes from negative to positive. So when we're looking at possible points for relative extrema, you have to see what the slope is doing. Okay, where is it changing from negative to positive or positive to negative? Okay? Yes? Good? Maybe? Questions about that? The other thing is if this thing has an open circle, okay, anywhere on the graph, okay, so if the function is not continuous or it's undefined at that point, then you cannot have any kind of extrema. So it's not considered a relative minimum or a relative maximum. Also, if the graph does not stop at some point. So if this kept going on forever and I don't tell you, this is not a relative minimum because it's going on forever in one direction. So if the graph is continuous this way, then it has no minimum. You could have a relative minimum, but you won't have an absolute minimum. Okay? There. Okay, so now, what do I have to tell you about? The extreme value theorem. The extreme value theorem. Extreme. And in the book, I didn't really talk about this, but they talk about that these things are, it seems like just numbers and stuff, but they're maximums and minimums are very important for optimization, which we talked about in chapter 4. How do you make a car that is at its maximum fuel efficiency when you have a whole lot of variables and stuff like that, okay? How do you, design something that holds the most with the least amount of material or something like that. So all these problems have very real applications. All right, so what was it? Extreme value theorem. You've already got so distracted. If f, which is some function, is continuous on a, b, then f has both a minimum and maximum on AB. Okay? So in order to ensure that a function has both a minimum and a maximum, it has to be continuous. That's what it says. All right? And some people said, like, what about this function, like y equals 2 or something like that. So if I have a horizontal line going across, does that have both a minimum and a maximum? Oh, on an interval from 3 to or -3, say up to 5? They're both the same, okay? So both the minimum and the maximum are the same. So if you have a straight line, it can have both. So both negative, the entire segment there is considered a minimum and a maximum. But if you have something else going on, so if you have this function, then it would have to have a minimum value and a maximum value on that interval if it's continuous. Now, if there's a hole in it, there's no guarantee that there's a minimum or a maximum. Okay? All right. Critical minimum, relative extrema, local extrema, parameter c equals 0.
So if there's a whole graph and there's no minimum.
Then there's no minimum or maximum. At least that there doesn't have to be both a minimum and a maximum. Yes. Okay. All right. So then, critical points. So critical points are points where something interesting is happening in the graph, okay? And critical points occur when f prime of c equals 0, or f prime of c is, I should call it critical values, not critical points. Critical values, f prime of c is undefined. So several types of critical values you could have. You could have like we talked about. So if this is c, you would have a relative maximum, okay? But you could also have things like cusps, where the derivative is undefined at c. But you could also have other things going on, like in a cubic or a, when do we see these things? If you do like y equals cube root of x, you get something that looks like this. And this is a case in which f prime of c, if this is c, that c is undefined, and yet the function doesn't have a cusp, and you don't have a maximum or a minimum there. Yeah, does anyone know what that's called, which we'll talk about in the third section? That point of inflection, okay? You could also have the derivative being 0. You could have the derivative being 0 without having a maximum or minimum there. What do you think? Watch if I have something like that looks like this, right? The derivative appears to be 0 right there, right? But I don't have a maximum or minimum. So you have to check what's happening to the right and the left at that point to see whether you have a maximum or a minimum. Good. I could also have asymptotes at critical values. So if this is c, I could have something going like this, and I have nothing going on there except for an asymptote, or something like that. So f prime of c is undefined, I could have something like that. So all kinds of things, and I could also have something called a plateau. Well, this is kind of like a plateau, but you could also even have functions that kind of start like this, and then they're flat for a while, and then they bounce up, okay? So you could have all kinds of things happening at these critical values, but what you need to do is check what's happening there, okay? So the first, and I already talked about that, extreme values don't occur on open intervals, meaning, so let's just do an example, which he does in the video. So say that f of x equals 1 over the square root of 4 minus x squared. So first of all, this thing is not defined everywhere. How would I find out where this function is defined? What's the domain of this function? That's why I ask you, sometimes I ask these domain questions. So to find the domain, what can this not be down here? 0. So you know that 4 minus x squared, it has to be bigger than 0, right? Not greater than or equal to 0, which a lot of you got wrong on the last test. Okay, because it can't be equal to 0. Why can't it be equal to 0? Because that would make this function infinity, right? So it's got to be bigger than 0. So if I solve this, I get negative x squared is greater than negative 4. Or I can say that x squared is less than positive 4, right? Which means, without doing the number line thing, what two values, can you think about this? What two values does x have to be between? Very good. It's got to be bigger than negative 2, right? Because if I went negative 3, that would make this 9, right? Which is not less than 4. Anything less than negative 2. Or it's got to be less than positive 2, because anything bigger than 2 would make this quantity. And so this thing is only defined from 2, -2 to 2. So this is called an open interval. I think it's just open interval, which means that at the endpoints, even if they're high and low points, which they are in this case, if I were to graph this thing, this one does look kind of like, it kind of goes like this, and then it goes like this. And this is the point -2, and this is the point 2. But since these are open circles here, okay, even though these appear to be relative maximums, they're not considered maximums because the circle it's an open interval, meaning it doesn't include the endpoints. Anyone have any ideas why I can't have a relative minimum or maximum there? If those are open. Yeah, because you couldn't really define it, right? You say, where is the maximum? Well, someone in the last class said, oh, it's at 1.9. So, well, what about 1.99? You know, where 1.99999. So, you can't really define it. So then, to find out, what we're asking in this question is find the extrema. So to find the extrema, that's a fancy word, right? All you have to do is take the derivative and see where the derivative is 0 or undefined, and then see what's happening at those points. And then if you do have a closed interval, then you would plug in points to that closed interval and on the endpoints and see what's happening there as well. But to do this, I'm going to take the derivative. So f prime of x. So what I'm going to do first is rewrite this, which you guys should do too, as 4 minus x squared raised to the -1, that rather than try to apply the quotient rule, because that's too much work. So -1/2, thank you. Okay. Who told me that? Thank you. Okay. F prime of x equals -1/2 times 4 minus x squared times -3/2 times the derivative of the inside, which is -2x, which a lot of you guys forgot to do on the test. Okay, you always have to take the derivative of the inside function. And then it looks like I could cancel a negative with a negative. I could cancel out a 2 with a 2, and I end up with a positive x over a 4 minus x squared raised to the 3/2. Right? Okay. Where is this thing? First of all, where is f prime of x equal to 0? You just set the top equal to 0 when x equals 0. So that's a critical value. We're going to explore what's happening there. And then f prime of x is undefined. Where? Where is f prime of x undefined? When the bottom equals 0. So when 4 minus x squared equals 0, which is at, if I solve this, I get at +2 and -2, but we already eliminated that from places where I could have extrema, okay? So even though the derivative is undefined there, okay, I can't have extrema there because that's not in the domain of my function. Do you understand that? Okay? So I don't have to worry about what's happening at those endpoints. Now, if I had something like they define the interval from -1 to 1, closed interval, they said from -1 to 1, like that, then this point and this point would represent absolute minimums and maximums. Do you understand that? Okay? So if they said on the closed interval from -1 to 1, find out the extrema, then I would have two maximums at those values. Yes, sir?
Do they have to be, for it to be a global extrema, does it have to be a function with no domain limits, or?
No.
So those wouldn't be local maximums and minimums?
they'd be local and they'd be absolute. Yeah. Yeah. Okay? And then at x equals 0, so you could look at the graph and tell it x equals 0, that's probably a minimum. But the other way that I could do it, which I don't think the guy in the video explained very well, is look at what's happening to the derivative at that point. So if I have x and I have f prime of x, if I take a number very close to 0, and just kind of do this kind of in your head, like to the left side, so negative, let's say negative 0.01, what kind of number is this going to give you out? If I plug in a negative 0.01, any kind of negative number, what kind of number am I going to get out? This is saying to the square, so it's always, what? Negative 0.01, this is going to be a small positive number, so 4 minus a small positive number raised to the 3/2 power is still going to give you a small positive number. This is going to be a small negative number. What's a negative divided by a positive? It's going to be a negative number here. So you don't have to worry about what the value is. All you have to worry about is the sign of the function. And we'll talk more. We didn't talk specifically about this because this is covered more in chapter 3. If I plug in a number to the right, very close to 0, like 0.01, this is still going to be a positive number, right? This is going to be a positive number. What's a positive divided by a positive? Positive. So the slope is negative here, even though it looks pretty flat, and then it's positive here, which means at this critical value right there, I must have a relative minimum, but it's also, since that's the only critical value in that domain, then it is also the global or absolute minimum. Global minimum. Okay? Yes? It's kind of tricky. Okay? So we got to do one with a piecewise function. And for this piecewise function, it has to do a logarithmic function. So with a piecewise function, you have f of x equals, you might have noticed that the calculus people like to give you piecewise functions, don't they? Because they have confusing things going on. X is less than or equal to 1, and x plus 2 if x is greater than 1. Okay, and they say find the extrema. Okay, so what do I do? Is this a continuous function? Is it continuous? Yes, it is. It's not completely differentiable, but it is continuous because look, if I were to plug in, so at 1, what do I get out when I plug in 1 in here? What do I get out when I put, oh, did I mess up? No, I messed up. I wrote down the wrong function. No, it's not a continuous function with that. It should be 2x squared there. Sorry, I screwed up. I wrote down the wrong term. If I plug in 1 in here, what do I get out? 3. So 1 gives me out 3. So there is a point for sure on this graph, 1, 3. If I plug in 1 in here, what do I get out? 3. And so this agrees with that. And so then what I get is going up from this point, I have a line with a slope of 1. So it's going up that way. It shouldn't be dotted. And then over here, I have an upside down parabola. Let's do pink again. Okay? I have an upside down. Oh, that's not what I want. I was trying to get fancy. See what happens. You look at the. I have an upside down parabola that looks like this. All right. So this should be a solid line. It doesn't need to be a dotted line for any reason. Okay. So based on this, now I'm going to take the derivative, all right? And so f prime of x looks like negative 4x if x is something, and it looks like 1 if x is something else, okay? Because that's a derivative of this and of this. So where is the slope of this line? Where is the slope of this equal to, where is it undefined? Where is the slope, where is f prime of x? Where is f prime of x undefined? At 1, because if I take 1 and I put it in here, right? At 1, I get out f prime of 1 is negative 4. If I plug in 1 in here, I get out this is f prime of this. If I plug in 1 into this part of the function, right? I get out 1, right? So this always has a slope of 1. And so at this point, since the slope changes abruptly from m equals negative 4 to m equals 1, the derivative is undefined there. And so I could have an extrema there. What kind of extrema do I have from looking at the graph? What do you call this? Yes, that's a local or relative minimum, okay? And then if I look at where this thing is 0, well, I use only this function, and I said minus 4x. Where is that equal to 0? Where's minus 4x equal to 0? Hello? Where's minus 4x equals 0? When x equals 0, and you can plug in a couple points near that, but over here I have a relative maximum, okay, or local maximum. I don't have any absolute minimums or maximums because this thing goes up forever and this thing goes down forever, right? And there's no limits on the bounds. But if I said, if I change this and I put like from x equals negative 2, and I did this from x is greater, and I went from 1 to 5 or something, then I would plug in those values at the endpoint and see which one gave me a maximum and a minimum. Thus, you understand that? Okay. And lastly, you're going to see some functions that look like, that look like f of x equals natural log of x plus x 1 over x. You're going to see one like this in your homework. And they're going to say find all relative extrema. And they'll give you an interval on this. Like say from like negative 2 to 3 or something like that. Hello? And you have to know how to take the derivative of this and deal with it. So let me do that really quickly. What's the derivative of natural log of x? 1 over x. What's the derivative of 1 over x? Good. X is equal to negative 1 over x squared, right? Because I could rewrite this as x to the negative 1, then when I take the derivative. Now if I simplify this, this is equal to, if I find a common denominator, equal to x minus 1 over x squared, right? Because if I multiply this by x over x, that's what I get. So this one is undefined at x equals 0, and you have a, it's 0 at x equals what? 1. And so therefore, in this case, you would have to check those 2 points to see what you have there. And then at the end, you have to plug in these 2 points and see if I get a number that is higher or lower than those 2 points. And if I do, that would be your absolute maximum or absolute minimum. You understand? So after you find the relative maximums and minimums or something that's going on there, Then you have to plug in these points and see what's happening at the endpoint, because those might be your absolute maximum. Okay? Because they always give trick questions like that on the AP test. Oh, I found all the relative mins and max, but you didn't check at the endpoints, so you didn't get the question right. You know, and so that's kind of what. Because I gave a problem to my pre-calc class. It's like the water temperature changes, and it goes like this, and it said something like, what is the minimum temperature? And the minimum temperature actually occurred like over here, and they all thought it was here because this point was a relative minimum, you know, but you have to check at the end point to see what's going on. All right, I think I'm done. Oh, other than showing you what the homework is, I showed you that already, right? But if you go here and to my Cutting Edge website under Chapter 5, and it's this page 198. So there you go. Now I'm going to stop.
Yeah.
And I talked